Yes, hello, good evening. So I think we can start the class today. Let me share the screen. Is the screen visible? I think so. So let us start with that. Am I audible? My voice is clear. Can you just confirm it if the voice is clear? Okay, I guess I can start. So today is the fifth class of our discussion, and whatever we have studied till now. Just a second. Remove this. So we have studied until now the configuration, conformations, okay, then naming. What else we have studied? Stereochemistry and acidity or basicity. So these were the preliminary things that we need to, clear our understanding before going into reactions. So I think some topics were pending. I told that I will discuss in the next class. So one was, for amino acid. So this was called isoelectric point. That I was a bit confused last day. So I am discussing it today. So let's say you have an amino acid. That means you have NH2 and then COOH. Okay. So these kind of compounds are called zwitterionic. Why? Because at the same time it can have same time the molecule can have positive or negative charge. How? So let's say you have for this nitrogen atom, this nitrogen you have pK of 9. Okay, somewhere around 9. And for this one, this group, this hydrogen, not for actually nitrogen, for proton. For this proton, you have pK 9, and this one you have pK around 2. Okay, so if your pH is greater than 9, then what will happen? Both will be deprotonated. So the you know configuration will be like NH2, then COO minus. So now you know that it is having 1 minus charge. Okay, this is the charge. So if your pH is less than 2, then you know that it will be protonated NH3 plus, then you have COOH. So what is the overall charge? That is 1 plus. And in certain case, if you have pH that is in between 2 to 9, in that case what will happen? So this one NH3 will be remain as protonated form, and this COO will be deprotonated. So now you know overall charge. Overall charge is 0. So how to calculate? So this term isoelectric point is the pH of the medium at which the overall charge of the particular amino acid is 0. To how to calculate that? You know that you have pK1 that is 9, pK2 that is 2. So the general rule is that Pi, it is denoted as Pi, is pK1 plus pK2 divided by 2. So this is the formula of isoelectric point. And now if you have, there are two subsections, so two cases. If you have, so one is you are having acidic R group, or side chain. So this is your R group. So if you have acidic R group, then you have, you know, NH2, you have another C double OH. So this is some carbon group is it there. You have another C double OH here and you have C double OH here. So now you have, this is pK1, pK2, this is pK3. In this case, how you will calculate? You will take the middle of these two, acidic one, pK2 plus pK3 by 2, because in this region only, in between pK2 and pK3, we will find that overall charge 0. And in the second case, you have basic R group like NH2, then somewhere here also some carbon, then NH2 and C double H. So if you have like this, then your Pi will be pK1 plus pK2 by 2. Okay, like this. Just it is depending on the at the pH where your overall charge will be 0. So fine. So today we'll go into the reactions and mechanism. So in this week we have started with the reaction of alkenes. Reaction of alkenes, right? So you know what is an alkene? So we have already discussed, which is having suppose C double bond C. This is a preliminary thing. This is ethylene molecule. So all these are sp2 hybridized, and how they are present. So suppose this is your plane of paper. This is one sigma bond. This is hydrogen, hydrogen, and then your pi bond is formed with the overlap of p orbital. This is the structure of an alkene. So now they are called alkene and alkyne are called unsaturated hydrocarbons. Why? You know, CH3CH3, that is called ethane, and between CH2CH2 or CH. So this is ethylene and this is acetylene. Or you can write as ethene or ethyne. So you can see in this case, this is the maximum number of C double bond H bonds that can be formed. Okay, this is maximum C double bond H bonds. Okay, so what you can see in this case, you are not having the maximum case. So these are called unsaturated. This is called saturated. So you may have, in daily life, you may have, come across this term, that is saturated fat, unsaturated fat. So it is always recommended that we should, consume saturated fat and not the unsaturated, because unsaturated will have this kind of, uh, bonds that are pretty much reactive. They can react in our body, in our system, so that will harm. Okay, so that is why people, tends to use more saturated organic molecules. So we need to understand some things. Property of alkenes. So as I told that alkenes are unsaturated in terms of bond, hydrogen bonds. So there is a term that is called degree of unsaturation. Okay? Or you can consider it as double bond equivalent. Both terms are valid. And how do you calculate it? So the formula is 2 into number of carbon, minus hydrogen plus nitrogen minus any halide present, and plus 2 altogether by 2. This is the formula to calculate the double bond equivalent. So you can easily get an idea that how many pi bonds that are present here. Okay, so this stands for pi bond, stands for number of pi bonds plus rings, if any rings are present. Okay. So then we'll move to the isomerization in alkenes, right? You know that a double bond, okay, that is fixed R1, R2, R3, R4. This bond cannot rotate, cannot rotate. Why? Because of because rotation will break the pi bond, right? Because pi bond is a side overlap. It is not a direct overlap. So sigma sigma is direct overlap, but pi is a sideway overlap. Okay, and that is why if you try to rotate the bond, then this overlap will be disturbed and the pi bond will be broken. So it cannot rotate. So that is why you don't have any conformational thing here. So conformation always, what I told, conformation always relates with the bond rotation. Okay, so if your barrier to bond rotation is small, that time conformational isomerism appears. So this is the case for single bonds, right? You have very less barrier to bond rotation. But in this case, for alkenes or even for alkynes, so your barrier to rotation is very high. So you cannot rotate your bond. Okay. So for this case only we have geometrical isomerism. Okay. So what is geometrical isomerism? So I can for example, let's say um, 2 butane. The 2 butane can also be written as but 2 in. So generally, what is the structure? Uh, you can write it like this, okay, or like this. So I'll show you the other ones. Here hydrogen is attached, here hydrogen is attached. Here also in both cases hydrogen is attached. Now what you can see here, these two groups methyl, they are on the same side, and here they are on the different side or opposite side. This is particularly known as cis, and this is known as trans. Okay, so this is the case where you have, similar substituents on both side of the double bond. So you have methyl and proton here. Here also you have methyl and proton. What if you don't have similar substituents on the both sides? So what if you don't have substituents on both sides of double bond? Hmm. So let's say this one. You have fluoro, then you have methyl, bromine, and hydrogen. Now you can see that all four substituents are different. So how do you decide the isomerism? How do you decide here? So in this case, what you need to do, for both sides, you need to give the priority. Hmm. So this bromine and hydrogen. So this priority will be considered upon the molecular weight. Okay. So bromine is having higher molecular weight, so it will be 1, proton will be 2. Similarly, chlorine will have 1, and in this case, carbon will have 2. Right? Now, what we can see, so the prior groups 1 and 1 are in the same side. So this is termed as, so there are two terms actually, I'll write it for you. One is called E. It stands for, a German word that is called antigen, and Z is another German word Zusammen. So this is antigen means anti, and Zusammen means sin. So now, if your both priority groups are on the same side, then it is Z, because as the nomenclature says. But if you have the different scenario like Cl, Me, and then H and Br. So this is 1, 2, 1, 2. Now you can see the 1 and 1 are in the diagonal relationship. So then this will be termed as E isomer. Okay. I hope you have understand. Or if not, you can get back to me. Now let's we move on to some systems which are having more than one double bonds. Okay, or a long chain like that. So CH3, CH, double bond here, C, H, CH3, CH3, H. Okay, so how to name this compound? Okay, you have to see that along the long, no, first point is considering longest alkyl chain. No? Double bond formed should come earlier Okay, that's how you should consider it. So if I consider it like this way, uh, 1, 2, 3, 4, 5. Now you see at which position double bond is coming at 3, right? Now, if the other way, if I am doing 1, 2, 3, 4, and 5, now the double bond is coming at 2 positions. So this will be my right choice. This will be wrong. So now I have to name the compound in such a way. So I have a methyl group substituent at 4 position. This will be 4 methyl, right? You have the double bond at 2 positions, so you can either write 2, this is 5, that means pent in, or you can write as methyl. Sorry, there should not be any gap here. 4 methyl pent 2 in. Okay, and then this one you have to uh, consider the geometry. Which isomer is this one? So for that you need to know that how this is uh, present in the space. So let me draw it like this way: CH3, CH, and then you have H here, and the other groups is CH3 and CH3, right? Yeah, that's fine. So here you have one group here, two group here. Here also one and two. So you can see one and one are on the same side, and the same side means what? Z. Okay. So this will be termed as Z for methyl pentachlorine. Okay, we can do another example. Another example. Let's say this compound, you have to name it. So you first think that you have to consider the longest chain where your double bond will come first. So I will number it such a way: 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now you can see you have methyl at 3 position, methyl at 6 position. Hmm? And what is the geometry of this one, of the double bond? Hydrogen is here, so that means this is 1, this is 2, this is 1, this is 2, because this is ethyl group, this is methyl. Okay, there are 2 carbons present here. So now you can see 1 and 1 are opposite, so that means it is E. Okay, name will be E. You have 2 methyl, so 3, 6 dimethyl, then up you have 8 carbon chain, up 3 in. Okay, so this is the way you should consider the isomers, geometrical isomers. So with that we move into the reactions. Reactions of alkenes. So first thing we'll study the addition reaction. This is the most basic reaction, almost preliminary thing that we should learn when we start to learn the reactions. So this is the addition reaction. So pretty straightforward. Let's say we take this ethylene and react it with HCl. So HCl means you have a polar bond between hydrogen and chlorine, and as this is polar, so this will be delta positive, this will be delta negative according to the electronegativity, right? And then what will happen? This bond, this has a electron density. This electron density will be attracted towards the hydrogen. So it will take the hydrogen and your Cl minus will be generated. So, and when electron density is attracting the hydrogen, so at one position hydrogen will attach. So like considering this one, so this is the new hydrogen will attach here, and in the other position, electron density is removed from that carbon, so there will be one positive charge plus bromine minus bromide, chloride. This will be chloride actually. So, just a second. Yeah, but it's not going. Let me write it down. So on the second step, what will happen? This will come and bind to this carbon. So you will have CH3, CH2, Cl. Right? This is a pretty basic thing. So now many things will come. So suppose you have some R group present. Okay, you have methyl. In case of hydrogen, you have some other groups, electron donating electron, withdrawing groups. So all these things will have some effect on the possible product. Hmm. So you need to know two terms here. Uh, so why this electron density is attacking the proton? Okay, so there are two terms actually that is called electrophile. Electrophile. Okay, so electrophile means electron deficient, and the counterpart is called nucleophile. That means electron rich. Okay. This is also noted as delta plus, electron rich by delta minus. Okay. So electron deficient species are maybe it can be H plus, or it can be carbon, uh, it can be any Lewis acid like that. So BH3, AlCl3, this can be. Okay. And electron rich compounds are what? Which have lone pairs. Okay. Water. You have ammonia. You have any N containing ligand. These are good. So you also have lone pair here. So like this, you can have hydroxyl ion, which minus any halide ion, X minus. So these are all electron rich. So what will happen? It will, uh, look to search for some sites which is electron deficient. So nucleophile always goes to electrophile. Electrophile does not come to nucleophile. This will be the direction of the arrow always. So same thing. This is your nucleophile. I will consider it as NO minus, and then you have H and Br. This is delta plus, delta minus, as I already told you. So this one will go and take the proton. This is the first step, and it will form a positive charge. So now, two way it can form the positive charge. So either the proton can attach here, and in this position there will be a positive charge, or there will be another scenario. Uh, the proton will be added in this position, and here you will have a positive charge. So now, uh, the major and minor, so stability, major and minor product will depend on stability of intermediate carbocation. So now you have to check the stability of the intermediate carbocation. So what you know, you have a carbocation looks like this. Suppose you have a CH3 plus carbocation. So it will be on the plane. There will be an empty pi orbital. Empty p orbital. Okay. And now, how this positive charge? So there will be some positive charge. How this one will be stable? So as you know, the stable species always goes towards electroneutrality. Okay, so there should not be that much of charge accumulated in any center of the molecule. So always the molecule should go towards neutrality. So if you have something, if you replace this proton by some other group, okay, that can donate some electron, or by some interaction, so that the accumulation of positive charge is stabilized. So then it will be very much benefit or good. So if you have any other scenario where you have the CH3 groups here and here. So now what they can do, first thing they have plus I effect. Okay, they can give electron density through the bonds. Okay, this is plus I effect. And another thing which is most interesting is that you have this MTP, that is positive, and you have three hydrogen, and this hydrogen means what? They have sigma bond orbitals. Okay. Yeah. So these are electron field orbitals. These electrons can have some polar interaction with the empty p orbital. Okay, but for that this has to be aligned. Okay, and this is called actually hyperfine interaction. Not hyper, sorry. This is called hyperconjugation actually. It's called hyperconjugation. For this, what happens? Your carbocation gets too much stabilized. So now you can see that this one, it is having here 2H proton, here 3H proton, here also 3H protons, and compared to this one you have H, and here how much? 1. So how many hyperconjugative interaction you expect? 1, 2, 3, and 4. For this one you expect 4, and for this one 1, 2, and here 6, that is 8. So this is much more stable, right? This carbocation is much stable. So this will prevalent. So actual product. So you have also this bromine minus, and it will come here. So major product will be methyl, and bromine. Right? This will be measured. So similarly, we move on to next example. Yeah. Suppose you are adding HCl. So what will be the major product you expect? So hydrogen will be added to here, and here plus HCl. This one you expect as a major product. Why? Because this intermediate will be stable. This will be stable, right? So you know that if you have any carbocation that is 1 degree, this is H, this is H, this is called 1 degree carbocation. This one, this is 2 degree carbocation. This is 3 degree carbocation. So you know here you have 9 hyperconjugation. Here you can have 6 hyperconjugation. Here 3 hyperconjugation. So 3 degree will be much more stable than 2 degree than 1 degree. Okay. So in terms of stability, we have to consider some more, few effects. So that is called reduced selectivity. So let's say you have a cyclohexene actually, and you are adding HBr here, and then similarly it will attack to the proton, and you will have two possible carbocations intermediate, or this one. Which one will be stable? This one will be stable more. So your bromine minus will go to attach here. Then you will have the major product as like this. This will be your major, as the other one. This will be minor. So we have to understand that how the reaction proceeds. Okay. So what the energy profile diagram says. Energy profile diagram. How do you realize? So for a general reaction, let me just draw it one more time. Which one should I repeat? Yeah, this one. have HCl. And first you are forming the intermediate. Intermediate is okay. And there is one more species involved, that is called transition state. Okay, transition state is a imaginary species. You cannot characterize it or trap it, but intermediate can be trapped. Okay, and this is imaginary, but it has a deeper relation to how we understand the reaction mechanism and how we predict the product. Okay, so if I draw the energy diagram, suppose this is your energy, potential energy, and this is your reaction coordinate. These are your reactants. So your reactants has a certain energy level. Suppose this one. Then what will happen? It will go through a transition state and come to a intermediate state. So this is your TS1 transition state. This is your intermediate. This is your reactant. Now, from here, you know that the Cl minus will go and attach here so that it can form CH3, CH3. This will also be CH3 and Cl. This is your product. So from here, it will come to another level, that is for the product. And this here will have transition state 2. You have some difference here, difference in energy. This difference is called as free energy difference, delta G0. Okay, free energy change of the reaction. And this energy from the reactant level to the transition state, this is called the activation energy. So how to draw, how to visualize the transition state? Let's say you have this compound CH3, CH3 plus HBr, and you are having at the end this compound. Okay, so now if we try to draw the transition state ME, so this bond is going to break. Okay, this one. So we can draw it as the dash line, and then from here, from this point, it will connect to the proton, and also this HBr bond is also going to be broken. So transition state always, uh, depicted as inside the bracket, and you have a double dagger. Okay, this is your transition state 1, and then you are going to the intermediate. Intermediate is what? Methyl. One more thing. So you have to donate the partial positive and negative charges here, because after you are forming the intermediate, here will be your positive charge. H, 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 And then going to have bromine minus. So this is your intermediate, right? And then the second transition state will be what? Methyl, methyl, uh, like this. It will be delta minus, it will be delta plus, and then H, and H. So this will be your transition state 2. Okay. Now next, uh, shift of hydride or methyl anion. Okay. To favor stable carbocation. Right. Let's say we have this compound and we are adding HBr here. So what will the major and minor compound? Let me first write it and then I will tell you. Okay. So of our understanding, whatever we have studied till now, we would have assumed that this one will attack here. So the carbocation will be formed at more substituted positions, right? So it should have been like this, positive charge here and this one. But now you can see that if bromine comes here, it will form the minor product. But the bromine is going to the another one, another adjacent carbon side. Why this is happening? What is the driving force behind it? So you have a hydrogen here. If this hydride shifts to this position, go to another another intermediate where you have positive charge on the terminal one. So this is 3 degree, this is 2 degree. And as you already know that 3 degree is more stable than 2 degree carbocation. So this will be much more stable. Okay. So now bromide will come and bind here. So eventually it will go to this product. Okay, this will be the major one. But this is called 2 to nitrate shift. Similarly, like hydride, you can also have methyl anion shifting. So I'll give you one example. You have this tertiary group present. You are adding HCl. What will happen? It will attack here. Then positive charge here. Hydrogen will be attaching here plus chloride Cl minus. Now you can see this particular methyl group. If it shifts to this position and carbocation gets shifted to the another, then what will happen? You will have a 3 degree carbocation which will be much more stable. Okay. Now your chloride can come and bind here so that it can give you here. Okay, you see this is the major product. And in this case of rearrangement, how the energy profile diagram will look like? Energy and reaction coordinate. How it will look like? how many intermediate you have? You have two intermediate, right? So you have a starting material. You are going to one intermediate, which is your primary carbocation. Then it is rearranging to another intermediate, and then your nucleophile is attaching and going to the product. So this is I1, this is I2, this is your R, this is your P, and you have three transition state, TS1, TS2, and TS3, right? This is how the energy profile diagram will look like for the rearrangement cases. Okay, and then another case is that stabilization via ring expansion. Okay, let's say you have this molecule plus HBr. So how it will go? So this one will attack that proton, and you see that the carbocation will be generated at this position adjacent to the ring, right? Okay. Now you have your Br minus here. Now you can see it has an option to shift the carbocation to the subsequent side, this one. But how it will do? It will take this bond and it will go here, so that it will expand the ring and it will form a five-membered ring. Here will be a carbocation, and now this bromide will come, and this will be your final product. So what are the driving forces behind this? One is to get, so I'll write it separately. What are the driving forces? One is forming 3-degree carbocation, and second one is releasing ring expansion. You know that whenever you are going from three-member or two-member towards higher analogs like six-member, second member, so you are releasing the ring strength. Okay, so this way the overall system gets stable. So this is one of the effect. Then stereochemistry perspective. So you have some application of stereochemistry, like wait one second. You add HCl here. You will get the carbocation as the higher substitute positions. So here you will get the carbocation, on other side you will get the hydrogen, and then you have your chloride. So it will come and bind here. But you have two position actually. So you will have, this is the empty p orbital. Cl minus can attack in this space also. It can attack in this space also. So if they are attacking at opposite sides, so there will be two enantiomers present. So let me draw them. You will have two enantiomer. First one will be this one, the opposite one. Okay. So this will be enantiomers. If some is R, so let us determine this one. One, this is two, three, and four. Okay. So if you just check it from the downside, one, two, and three, they are rotating anti-clockwise. This will be R. So this will be S. What we can see in the mixture, you will have 50-50 ratio. So actually you will observe that this mixture will have no effect actually, no optical properties. So this will be racemic mixture, no optical response. Okay, so what we can understand from here, this electrophilic addition of alkenes are not stereoselective. Right. So these we were talking about, electrophilic additions. Now we will see some other kind of addition. So let's say you don't have HBr, you will have only Br, Br and Br. Then uh, this is not straightforward kind of polar interaction, but this electron density of the pi cloud, this can induce polarity in the nonpolar molecule. So this will be induced polarization. For HBr you have inherent polarization in the molecule, okay, inherent dipole. But here dipoles will be induced from the pi one. So what it will happen first will form like this. Let's say here you have some hydrogen, here also you have some hydrogen. So if hydrogen is on the top, then bromo will come at the bottom, and here you will have some positive charge. This bromine has some electron density, and it will go here and form a trinuclear ring that is called bromonium ion. So this is called bromonium ion. Now the next bromine, when it will come, next bromine minus, when it will come, it will attack at the less congested position. Okay. So what will happen? will have two bromo present, but this one exactly will not be the same. So if this will be trans actually, so if one is in the below the plane of paper, one will be on the top. This is how bromonium ion mechanism works. So typically we use solvents like tetrachloromethane for this kind of reactions. If you see in the conformation in 3D, it will be look like this. So this will be trans, okay? Or the more stable form is when this one is in the equatorial form, right? Or you can view it another way. Now, what you can see here, depending on the relative, direction of attack, electrophilic attack, okay? So you can have two different enantiomers. So these are enantiomers. You see? No, this will not be enantiomer, but you will have two different stereochemistry. So here you will have 1s and 2s. Here we will have 1r and 2r. This kind of stereochemistry will get it. So in CCl4 you will have bromonium ion formation, but if you use some other nucleophilic solvents, then what will happen? Let's say I am using bromine in water. So first thing is same bromonium ion formation will happen here. Now in the second step, you have two competing anions. Okay, one is bromine and one is water. But this is much more concentration because this is the solvent. Okay, water molecules are much more in number, so it will goes it will go past the amount of bromide and it will bind to the carbocation. So what will happen here? So it will take some time for stabilization such that your bromo will be here and here you will have some carbocation generated and this water will attack here and you will get so that depends on which side of the carbocation water will attack. So I'll just show one way. So H2 plus, then you will have methyl at the bottom and then bromo. And the next step, one proton will be eliminated minus H plus, so that you will have H methyl and bromo, right? So this is, you can see that oxygen this hydroxide and bromide, they are empty to each other. Okay, so this is called anti-addition, right? So this is a regio-specific addition. So what you can see that electrophilic addition of Br2 in water is regio-specific, and addition of Br minus and which minus NT to each other, and also stabilization of the carbocation intermediate is necessary, right? So with that, let us move to some questions about the same topic. So let me see how it is going on or not. Somehow I got disconnected. First question is the hybridization and geometry of methyl carbocation. So as you know that all the substituents, they are present in the planar position, and you have a empty p orbital. So this is actually sp2. Hmm? So sp2 and trigonal planar. This is the answer. So this will exist at exact 120-degree angles. So the first question is right. sp2 and trigonal planar. Next question is what type of reactive intermediate is formed in the reaction of an alkene with bromine and water to be bromohydrin. So I missed this one. So this kind of reaction is called, we have to H2 is called a bromohydrin reaction. Hydrin reaction, right? So here the reactive intermediate is actually a carbocation. Okay. Or just a second here. I think it will not be the carbocation, it will be the cyclic bromonium ion, because as we see that first one form this kind of intermediate. Okay, so this is your intermediate, and then you will form which will come here, or H2, just a second. H2 will attack here and then it will form this one, right? So this one will be the answer. Then we move to the next question. What is the major organic product obtained from the following reaction? Okay. So as you know, this is a case of 1,3-methyl shift. So let me just draw it. First, the carbocation will be formed here. Okay. You have iodine minus in the system. And then one of the methyl group will shift here so that your carbocation will shift the other side. So then you will have, okay, here is the positive side, and then your I minus will bind here, and you will get the desired product. So what will be the answer? I think option 3 is the right answer. Yes. Then we move to the next question. Which of the following is considered as allylic carbon atom? So these carbon atoms which are adjacent to the double bond, these are called vinyl. Hmm. This one is called allyl. Okay, so two position will be the right answer. Moving on to next question, assign E or Z. So to assign E or Z, we know that we have to prioritize on both sides of the double bond. So Cl will be 1, this will be 2, this will be 1, and this will be 2. How? Because it has another carbon atom attached to it, and this is only hydrogen, right? So now you can see 1 and 1, they are opposite. Okay, so opposite means what? E, right? So the right answer will be E. Now we go to the next question. So, which amongst the following is not a structural isomer of the compound C6H12? For that, we need to calculate the degree of unsaturation. So, I have already told you the degree of unsaturation. So, what is the formula here? 2 into carbon minus hydrogen plus nitrogen minus X plus 2 by 2. So, let us do it. Number of carbon is 6, 2 into 6 minus hydrogen is 12 plus 2, then 2. So you have 12 minus 12 plus 2 by 2, this 2 will cancel out, then you will have 1. So degree of unsaturation is 1. That means it should have 1 pi bond or 1 ring. So what you can see here, these have one ring that is satisfied, these have one double bond satisfied, this is also having one double bond satisfied. But here you have ring and double bond both. Okay. Then here your double bond equivalent also it is called Db is 2. So this is not correct. So first one is not a structural isomer of C6H12 because the double bond equivalent is more in case of 1. I hope you have understand. Then move to the next question. So it is told to assign E or Z to the following alkene. Okay. So for that same thing. So between chloride and sulfur, which one will be the you know uh, high priority depending on the molecular weight. So let us finish this one. CH2 and CH3. This will be 1. This will be 2. Okay. And for chlorine and sulfur, chlorine will have 1 and sulfur will have 2. Okay, then as both groups are on the same side, priority groups, this will be Z. So this will be right answer. Okay. Which alkene gives meso compound upon reaction with Br2 in dichloromethane? Okay. So let us see. Z2 butene, Z2 butene. So Z means the priority groups on the same side. This will be Z. Priority groups on the opposite side will be E. 2-methyl but 2 in methyl but 2 in. Yeah. And then you have 2-methyl but 1 in. 2,3-dimethyl. Sorry, with the right structure, check it. Yeah. 2,3-dimethyl but 1 in. Yes, this is the right structure. So now we have to check which one will give meso compound upon reaction with bromine and dichloromethane. Okay. First, let us check with uh, Z. Br2 CH2Cl2. What will happen? First, it will form the bromonium ion. Let me just draw it in this way. Then the bromide ion, it will come and attack at any of the position. Then we will have this will be from then on the opposite side each. um, so now you check it. Does it form a meso compound? So for meso you need to have for meso need need a mirror plane. Okay. So now you rotate this bond so that you can find at 180 degree and then see what we can find here. If bromine goes down, then what will happen? Here will be your H and here will be your methyl group. So it is not forming a meso compound, right? For the second case, let us do with this one. And then we have to what will happen first. This one will be okay. So let us do it this one. Suppose we are having like this. Okay. Then bromine minus will come and now it will attack through the other position so that you can have Like so now you can see that uh, all of the hydrogen, say bromine or the methyl, they are on the opposite part. Okay. So now if I rotate this 180-degree, what will happen? That will go here. So methyl will go here. Then bromine will come on the top. Okay. And then hydrogen will be at the bottom. So now you can see you can have some sigma plane. Okay. So that is why it is called the meso. So you have stereo centers present both sides, but they will racemize internally. So this is a meso compound. So this will be possible for the E. Okay. So as we have already find out the correct options, so we don't move forward with the other options. That you can check it later. So the next one, what is a major organic product obtained from the following reactions, right? So same thing we have to do like this. First, what is the intermediate that it will generate? So let me draw the bromonium ion on the top. So this is one case. Another case will be when the bromonium ion will be in the bottom. And then it has to go to a rearrangement where this will be positive. Here also same thing. Now water will attack. So it will come through the bottom because bromine is on the top, and in this case it will come through the top because bromine is on the bottom. So next you will have proton will be removed so that you can have the final product, that is which is on the top, methyl is on the bottom. Here also you will lose the proton. Then the final product will be this one. So which one will be the right answer? I think 3 and 4. Okay. So this one will be the right answer. So we move to the next question. What type of reaction mechanism accounts for the reaction of an alkene with HBr to give an alkyl bromide? Right. So this is actually electrophilic addition. We all studied, right? Then what is the major organic product obtained from the following reaction? There is a shift will happen, and this position the iodine will attach, or the water will attach. So the right product will be 4. Okay, I guess you understand. Then the reaction Q6. So we'll move with this reaction. The reaction in Q6 goes via cyclic carbocation intermediate, formation of 2-degree carbocation, 1,2 methyl shift and formation of 3-degree carbocation, and 1,2 methyl shift and formation of 2-degree carbocation. So we have to check it here. So you see the intermediate step will be here positive. So this will be 1,2 shift, like 1,2 methyl shift. Yeah, and what is the carbocation that is generating? This will be a 3-degree carbocation, right? 3-degree button generation. So the right answer will be 1,2-methyl shift and formation of 3-degree carbocation. This is the right option. The energy profile diagram of the reaction in Q6 will have the following number of transition states. So as I told you, there is a rearrangement here. So it will follow the same pathway like this. You have a reactant, TS1, then intermediate 1, then it will go to intermediate 2 and then to your product. TS1, TS2, TS3, then I1, I2, these are two carbocation, this is reactant, this is product. So what is the question asked? Following number of transition states. You know there are three transition states. So this will be the right answer. Move to the next question. So select E1 bromo 1 chloropropene. Okay. So just check it. So for bromine and chlorine, bromine will have 1, chlorine will have 2. Okay. Then this one methyl will be 1, this 2, 1 same side. This will be not same side means it will be Z. Yes. This will be Z. This is 1, 2, 1 and 2. This will be E. This will be 1. This will be 1. 1 will be E. 1 and 1. This will be Z. Right? Now, 1 bromo, 1 chloropropene. So bromine and chlorine has to be on the same side. So only B and C are E, but out of them, this B structure has bromine and chlorine on the same carbon atom, right? So this one will be the right answer, B. So moving on to the last question for today. So in the following reaction, the products A and B are. So let us do the reaction here. Each here. So first carbocation will form, and here bromine can attack either from this position or in this position. Okay, so that they will generate each beer or beer each. And these two are mirror images. Okay, these are enantiomers. So this one will be the right answer. Okay. So I guess we are done for today. Next class we'll do some more about different reactions of alkenes, okay, and other systems. So if you have any doubts, you can contact me. So today we'll stop the class here. And, yeah. Okay. Thank you.